Okay, welcome back to CS532W. My name is Frank, and today we're going to review Monte Carlo and Markov chain Monte Carlo, trying to make sense a little bit of the mess I made of talking about graphical models so far, but really talking about general purpose inference algorithms for graphical models, skipping over the fact that you might want to write a graphical model and you might want to apply a graphical model style reasoning in your application. That was our attempt up to this point, but that will come over time. But what we're going to start today is some of the sort of technical work towards operationalizing, like working with graphical models. And then we'll, after we're done with this, talk about old school inference and a nasty problem just one more time. And then we'll move to programs, and we'll move to compiling programs to graphical models, and then we'll move to generic implementations of inference algorithms in those graphical models. So I'm going to use the word inference a lot, right? And I think I already have, probably. So for those of you who can, especially, I don't know how to pronounce Ige Limbo, maybe Ige? Yeah. If you can turn your cameras on, it would be preferable so I can see. Yeah, thanks. Ege?
Yeah, it's
okay.
Fine.
Thank you. It's my first encounter with that name, so I apologize. It's a cool name. So what is inference? So again, we talked about what supervised, unsupervised models are, so on and so forth, but in probabilistic modeling, a model corresponds to some specification of a distribution of either data-given parameters, which is to say some conditional density estimation task, D given M, or a joint distribution of the data and parameters, which is the joint distribution of D and M, which decomposes as a likelihood times some sort of a prior. And we could go on forever about this, but we'll talk about unsupervised modeling or whatever. But basically, whatever we have, this could be sets of xi, yi pairs for some supervised model or whatever, and this could be a regression parameter that we're regularizing, or this could just be data, whatever the data is. So whatever your data is, it's there. M could be a continuous set, it could be a discrete index over models, and more to the point in this particular formalism, there could be latent variables that we integrate out in order to get this likelihood or evidence. Okay. But in particular, when we think about this particular form, learning, inference, and prediction can uniformly be cast as simple in scare quotes probability calculations. Right, and we know Bayes' rule tells us the probability of a model given a set of observations is proportional to the likelihood of the observations under the model. That's this likelihood, P of D given M, times prior probability of the model, which is P of M. Okay, so by the way, if you haven't figured it out yet, when I made this slide deck, I made a small error. These slides are supposed to go on the last slide deck, but I want to go over them again because it's where I was a little confused where these went. But anyway, so what do we do with the posterior or joint or whatever? Well, we can do model selection, right? So we can do literally model selection. We can take an argmax over the models given the data, which because of Bayes' rule, we can turn around. And this is actually how we do, model selection in the Bayesian context, right? This could actually be an indexed set of models, right? How many clusters are there in your mixture model, right? And you want to compute the probability of the data given that model, right? Or this could be a continuum of models in which you have a prior over weights in a regressor, and you have a likelihood given those of your data given those weights, and you want to select over an entire set. Alternatively, so if you haven't heard of Bayes factors, that's basically how you think about Bayes factors. You do model selection by counting through an indexed set of models, and you compute an evidence, which is this term right here, the probability of data given a model. Okay. You can also use this for posterior predictive inference, right? So out of your set of possible models, you want to form a posterior distribution, or you want to estimate, computationally characterize a posterior distribution here, and use it to predict something about new data D prime. Okay, so this was the out of sample regression example before, where we said, okay, well, can we computationally characterize a posterior distribution in some model given data? And if we do that, then we'll be able to do posterior predictive inference that is better calibrated in terms of uncertainty representation. Okay, and the Bayesian approach to what you would do in frequency statistics, where you compute p-values and do hypothesis testing, is instead actually to integrate test functions against your posterior. So if you want to say whether or not like a particular regression parameter lies in some range, or you'd like to compute the probability that some integration parameter lies in some range here between A and B, well, the way you frame such questions and answer such questions is to first computationally characterize the posterior distribution in some way, and we'll talk about lots and lots of different ways of doing that, and then estimate the value of this integral somehow, right? And we're going to talk about lots of computations that allow us to do that, right? So to answer a statement like, what's the probability that the weight on smoking being a positive factor in predicting the probability of lung cancer, what's the probability that that's between, it increases your risk between 2 and 3, well, you put 2 and 3 in here, and this is the risk parameter, and this is the probability of the parameter lying in some range, given a whole bunch of observed data about how much people have smoked and whether or not they got lung cancer, something like that. Okay, that should make sense. So Bayesian approaches to hypothesis testing look like this. They're in particular, they take the form of integrating some test function against the posterior. So posterior predictive, you integrate against the posterior, the likelihood to tell you something about how new data is going to be generated, right? Hypothesis testing, you integrate a test function. What is bold I? Bold I is a function. So if theta is on the real line and A and B, so we'll call this an integrator function. That's super awesome that you asked that question. Thank you. This function is a step function, which evaluates to 1 when that condition is true and 0 otherwise. Okay, so it's a set indicator function, basically. Great, awesome, cool. We'll use this kind of notation a fair amount. It'll become secondhand pretty straightforwardly, right? And of course, just to be clear, right, if there is some distribution over theta, like this is P of theta given D, right? Then when you multiply these two together, all of this goes away and all of this goes away. And what you're really actually computing is, the area under the curve here, which is, of course, when you have a density function, the probability that a parameter value or whatever lies in some range. Okay, cool. How come the delta notation isn't used? So, we're going to use, that's a good question. So we're going to use a bunch of different notation semi-interchangeably. So if we were to do this, then we would have a Dirac function, which has an argument here, which would be theta minus, yeah, I mean, I guess it would be, how would we do that here? I guess it would, the Dirac function is 1 when its argument is, how does it work? 0, right? So it would be 1 minus I of this, right? If you're going to use the standard like physics Dirac, we're going to use atoms. Usually we will use these to refer to atoms. So literally there'll be an atom, right? Like some particular value of theta, and this will be the Dirac mass at a particular atom, right? So when we use Dirac notation, we will associate it with a particular atom. And when we talk about set membership functions, we'll just use this indicator function. And although I'll be a little bit lazy, it'll be clear from context. But good question. Okay. So here's the problem, right? So if you've done machine learning for any period of time at all, then you know that that we're really good at computing d whatever of f of x, right? Equals whatever. That's what machine learning people do. We take derivatives and then we use stochastic gradient descent. We're really, really good at that, right? But there's this thing here which should be fairly evident. It's this thing, right? It showed up there. It showed up here, right? And actually, when you compute, P of m, when you compute this thing, it's got a, wow, can you see that? Oh, that is a terrible color. This thing, P of m given d is equal to, P of, d given m, P of m, over the integral of P of d given m, P m, dm. And guess what? There's this integral here as well, right? And like machine learning people and everybody, like we all know integration is hard. That's the hard part. Differentiation, easy. Integration, hard, right? I mean, we know this even from, high school maths or whenever it is that you first started learning about integration, right? Derivatives, easy. Integration, hard. This course is largely about integration. Okay, actually, at the end of the day. If the prior is uniform, does this hypothesis testing approach, is this equivalent to the frequentist one? The answer is no, and well, okay, it's not. The answer is rather subtle, and this will derail us for a second. The answer is, here are several answers. One, you can't define uniform priors over any continuous domain. Okay, so straight away, you're done because you can't integrate to one over. Okay, you can have uniform over bounded. You can't have uniform priors over unbounded continuous domains. Right? Sorry, I apologize. I apologize. Right? That's the first thing. Second thing is, if you have an uninformative prior, then there are uninformative priors. So I'll just say there are uninformative priors. They're known as Jeffreys priors. The third answer is that there are well-known asymptotic results for Bayesian statistics that say that estimation in any Bayesian model under an infinite stream of data results in a collision. In parametric models, results in a collision of the estimate under the Bayesian model and the frequentist model. So maximum likelihood and Bayesian inference collide when in the limit of infinite data in parametric models. That's known as the Bernstein-von Mises theorem. But the fundamental mechanisms of inference between frequentist inference, which involves repeatedly estimating the sampling distribution of whatever estimator you use, and the distribution and the Bayesian distribution, those mechanisms are different. So very rarely are the posterior uncertainties and confidence levels aligned because they actually mean different things, right? One is, how does your estimator vary under different data sets, right? And this one is, how does your parameter value vary given a single data set and your prior beliefs? Those two quantities are not really interchangeable, right? They're beliefs somehow, and you can get confused about that, but yeah. Okay, so integration, which I'll often colloquially, we'll talk more about marginalization because that's generally it requires integration, but you should just think when you hear marginalization, it's integration, right? Is generally hard. So if you have simple analytic functions, you can look them up in your favorite calculus textbook. I'm motioning at my bookshelf in front of my desk now, right? You can, look them up. apply various rules, so on and so forth. Numerically, if you have low-dimensional well-behaved functions, you can do kind of quadrature kind of things where you evaluate the function at various points and effectively build, parametric approximations of the function that you can compute the area underneath the curve for, right? For various nice functions, like the HMM example that I gave before, like you can do various integration things via dynamic programming or message passing via some product or something like that. And everything else, if you're lucky, you can still do kind of high school math things in Bayesian statistics, particularly in the exponential family and exploiting conjugacy. So we'll do a couple examples of that. And homework 1 requires you to understand what we're about to talk about in this way, right? And beyond that, it becomes numerical, basically, right? And there are lots of different ways. One very, very important family is sampling-based approaches, Monte Carlo-based approaches, Markov chain Monte Carlo-based approaches. That's what we're going to talk about largely today. Sequential Monte Carlo is in there. We'll talk about that at some point during the course. Or learning various approximating functions that have nice properties that make integration easy. In other words, if you approximate the posterior by some functional family that factorizes across the dimension, which is known as a mean field approximation, then integrating against such a posterior distribution, which is approximate but easy to work with, is easy. We'll return to that. Okay. Cool. So, of relevance to the last problem in homework 1, and I think, oh yeah, there's I think even an exercise early on. Was it Poisson and Gamma? I can't remember which one I stuck in there. There's a million examples. Is that I want to encourage you to understand both sort of the mechanics of Bayesian. So, like, what's homework one about? It's making sure that you actually know what's up with Bayesian inference, but also experience firsthand, because many of you have not, the pain and horror of having to actually write and derive your own samplers for various models, right? This is the most effective way to get you to become a probabilistic programming acolyte is basically to force you to do it the old school way before you do it the new school way. So that's it. So let me give you one example of the kinds of integrals that you can do using understanding about Bayesian statistics, in particular, understanding how various distributions must normalize. So in effect, what these next few slides are going to do is expand your lookup table of integrals that you can perform analytically. Okay. For the programming languages people, or people who are used to this, there are project opportunities here straight away in terms of Rao-Blackwellizing various samplers, general purpose samplers, by inspecting graphical structure and doing some of this marginalization and integration analytically as a program transformation rather than as a numerical operation. Okay. So you can get fancy with this stuff real fast. Okay, so I've at several points already talked about Dirichlet distributions, right? So recall that if some vector theta is Dirichlet distributed with some, what often is referred to as a base distribution alpha, then the probability density function governing theta looks like this. Okay. I think I see somebody typing a question. You might as well just say the question at this point. So,
yeah. Is the staple a denominator of pi for product?
Yeah, this is a product, yes, and this is the gamma function, which has a recursive definition. And what you should, I guess, I should put this in here. The space, it's the Dirichlet distribution is a really awesome distribution, right? Theta is is a member of the k-1 dimensional simplex. Okay, so the Dirichlet distribution, it will do in 3 dimensions. So if we have basis vectors of this, this, and this, right? The simplex is this surface right here, right? This is the set of all vectors whose elements sum to 1. A vector whose elements sum to 1 is a probability distribution, right? Okay, cool. Which means that a Dirichlet distribution is an analytic distribution that allows you to express your beliefs about what a probability distribution should be. Okay, so these values of alpha here, in particular, the parameters of the Dirichlet distribution, are your belief. And the larger those values of alpha are, the more concentrated the Dirichlet distribution is about that prior belief. So different distributions on the simplex might look like this. They kind of look Gaussian bubble-ish, but confined to the simplex. Or you can have distributions on the simplex, and this is pointing out of the simplex. You can have distributions on the simplex that look like this, so on and so forth, right? So basically, it has to integrate to 1 over the simplex, right? And there's the concentration, like how pointy how peaky the distribution is, right? You can have a very, very, very narrow, very peaky distribution here is controlled by basically the magnitude, basically the variance of theta is like I don't remember the proportionality, so this is very wiffly waffly, but it's proportional to, in some way, the magnitude of the alpha vector. Okay.
Is it fair to say that the Dirichlet distribution is in some sense like a beta distribution, but in more than 1 dimension?
I think it's better to say that a beta distribution is a 1-dimensional Dirichlet distribution, yes. But yes, indeed, exactly. Okay. So, so a discrete distribution should be relatively straightforward, right? Discrete distribution is just going to be a distribution parameterized by k values here, theta 1 to theta k, right? So the probability, so p of zi equals k is theta. Am I using subscripts? Yeah, k. Okay, so that's what a discrete distribution is. Now we have some model, right? We have a discrete population. So it could be, all of our ages, right? In actual years, right? And now we want to estimate the probability distribution over the ages of people who take this course. We have some prior belief about the ages of people who take graduate courses at UBC. In this parameterization, that would be alpha, right? So this is alpha. That's a mistake in the slide. This is alpha, and each one there's k of these alphas, right? So that's our prior belief about the distribution. So alpha might look like 20, 40, something like that, right? And then we have draws from the underlying distribution. So then we generate an actual distribution from this, which is going to sum to 1. This does not, the alphas don't have to sum to 1. There'll be some distribution. Maybe it's a weird draw, 20, 40. This is theta. And then we actually have our draws. Okay. Now the question is, there are a couple of questions, like, can we sample the age of a student under our updated belief about the distribution over students? Can we build the generative model for the ages of students for this class, the next person who joins off the waiting list or whatever? Or can we actually characterize the posterior distribution over theta, like what is the actual distribution given observations. Okay, cool. So we've got this Dirichlet distribution. And we know the discrete distribution. So what can we do? Well, if we want to predict the, the age of the next person in the course, something like that, I guess I should really be talking about topic models. That would make more sense, right? So, so theta is a distribution over words. Z is a word. Okay, and we have some distribution that we some belief over over what words should be in a particular topic. So theta is a topic. I don't know if I said that. So distribution of words is a topic, right? And then, yeah, great. Fine. So if we go with that, then we can ask what's the next word going to be in the topic if we draw another word from our updated belief about what the topic is, given that we've seen all of these words in the topic, right? Then that is a posterior predictive problem. We need to estimate the posterior distribution, and we need to integrate the likelihood over that posterior distribution in order to produce a posterior predictive. Okay. Okay. So if we're going to do this, let's establish a little bit of notation, right? I'll go back to my favorite pink color here. So let nk be, here's the indicator function that people were after. So we have some collection of data, right? We have Z1 to Zn. These are words 1, 52, whatever. Okay, these are words that we have. Let nk be the sum of 1 to n of the indicator function that zi equals k, which basically says we're going to count up how many occurrences of a particular word there are. Okay, and note that in order to form this posterior distribution, which is the first thing we need to do, that we write down the form of the posterior distribution as the likelihood under the discrete distribution times the prior, which is Dirichlet, given the forms before, right? And that looks like it's proportional to, we're using proportionality, so we're ignoring normalization constants for the moment. That looks like, if we flip back to the Dirichlet distribution, well, if we ignore the normalization constant, we have the form of the Dirichlet distribution here, right? So that's this bit right here, yeah? And we have this, right? So P of Zi equals K is theta K. We're going to have as many thetas as there are instances of the word, right? So for every theta K, we just have as many of them as there are instances of the word, and we just multiply over K rather than multiply a bunch of indicator functions over N, okay? Fine. Now, if you multiply these together, and I won't do the algebra because it's kind of boring and obvious, like there's a theta 1 to the n1, a theta 2 to the n2, so on and so forth. So that basically means that there's a n1 in here and an n2 in here and an nk in this exponent, right? Squint just a little bit. And if you see that, right, then you recognize that that is the form of an unnormalized Dirichlet distribution, right? That makes sense? I can't see. Does that okay, right? So voila, and this is where this analytic integration happens. This is where it happens, right here, right in between here, right? In order to go from here to here, you have to have solved an integral. What integral did you have to solve? We've got 1 over z. This is proportional to 1 over z of theta 1 to the n1 alpha plus alpha 1 minus 1 theta k to the nk plus alpha k minus 1. Okay, so that's the distribution. So what is this z? Oh no, we got nothing. This is bad. Okay, but if theta given the set of z's, right, is proportional to the joint over this thing integrated over theta. Right? But that's the normalization constant for a Dirichlet distribution. So you actually know the value of the, and this is the critical part. This is the thought-provoking thing, right? If you integrate this thing, if you integrate that d theta, that's equal to 1 over that. Because it's normalization. Right? So we've done an integration, and we've identified that we can actually compute the posterior distribution. We can do that integral because it's a Dirichlet, it's proportional to Dirichlet. We can identify that it's a Dirichlet. Great, awesome, cool. This will become a little bit more clear even in the next slide. Okay. When we do the posterior predictive, okay, so we've just derived that. That's a terrible color again. Tell me not to use that green color. We've just derived that this is Dirichlet. It's an updated Dirichlet with updated parameters. Okay, the posterior distribution, we did some analytic integration automagically by looking it up. This thing is still a likelihood. Okay, so now here we'll write down the updated, so this is the normalization constant for the new Dirichlet. This is the likelihood of this term. Yeah, okay. So if you have the likelihood of this term, right, well, what all this does is this thing goes inside of one of these. In fact, it goes in this one right here, for instance. Okay. And we still have to do this integral. We have to integrate over the parameter space, right? So we have the old normalization constant here, but we have this crazy integral, and this is this is how Bayesian statisticians do integrals. They're the only integrals that Bayesian statisticians can do, non-numerically, right? You look at this and you say, oh wait, that's just actually another Dirichlet distribution, but what we're doing is we're estimating the normalization constant for that Dirichlet distribution, right? Because you look at this integral and you say, aha, that's the form of a Dirichlet likelihood, right? So if I integrate that thing over theta, it has to normalize. This distribution has to normalize, so we know what the result of that is. This integral evaluates to this, the inverse of the normalization constant, right? Cool. The normalizing, yeah, the normalizing, yeah. So the normalizing constant. Let me make, if that wasn't clear, if it hasn't become clear, right? This distribution right here, this is the critical part, Adam, I think, right? This is a distribution over a probability vector, right?
I was just answering the question with little confidence.
Oh. Okay, great. Sorry.
Yeah.
Awesome. Okay, and it's true. This is a relevant point. Using facts about the gamma function, like you can go on and simplify this, and it ends up just being a ratio of counts. It's this simplifies dramatically. I'm not going to go through the simplification. It's ugly, and you can do it as part of your homework. It's not hard. Cool. But the main point is, and what we're talking about is integration for two things, for normalization and for posterior predictives here. So how do you compute a posterior distribution? Recognize that computing a posterior distribution involves this marginalization step, and this marginalization step happens here, and we do it by identification. And the reason why we can do this in this particular case, the only reason why this is doable is that the discrete distribution is conjugate to the Dirichlet distribution, which means that the posterior distribution stays in the same family. So when you update using a multinomial discrete distribution, your Dirichlet prior turns into a Dirichlet posterior, and then you can update it again, and it turns into a Dirichlet posterior, and it just stays in the Dirichlet family. So there are lots of distributions that have this characteristic. The Poisson and gamma are conjugate to one another. The normal is conjugate to itself, so on and so forth. And exponential families tend to play nicely with one another. Most distributions, like the kinds of stuff that we'll talk about later on in the course when we have normalizing flows and other kinds of crazy stuff like that, do not have this property, right? So we're going to be out of luck, basically. But it's worth knowing that it's worth knowing a couple of things, right? One is that in order to actually form a posterior estimate or to normalize a distribution, right, you need to do an integration, right? And maybe even more to the point, if you're going to do some sort of posterior predictive inference, you also need to perform an integration, right? Fine. This I'm not going to go over. This is just an example exactly like what we've already talked about. It's just a made up example to put words on each of the things. Okay, this one we're going to talk more about framing problems now, and then thinking about them in terms of integration, trying to convince you that integration is, even though hard, necessary and interesting for our purposes, right? So yeah, so this is very similar. I think we basically discussed this, but we did it super fast last time. We have some data vectors lying in some super high dimensional space. Here, super high dimensional space is 2, just to make things easy, right? I would like us to collectively ask and answer the question, is this point similar to this point? Should we treat them as the same? Or equivalently, for any pair of points, is this point similar to this point? How would we go about doing this in a generative, Bayesian generative modeling capacity? What kind of model might we write down? Quickly now.
Some sort of mixture of Gaussians.
You could do this with a mixture of Gaussians, for instance, right? So you can impose a generative model that says, okay, let's say, again, I wrote this out very sloppily last time, and I'll probably screw it up again because I'm just, who knows, right? So there'll be Zi from some distribution, some discrete distribution pi. We've just done a Dirichlet distribution, so we can be really fancy about this. We could do Dirichlet alpha for pi, so we can like express a belief, but maybe not know what the distribution over classes is. So this is going to be the class identity for each one of these things, right? And then we'll say xi given zi will be distributed according to some distribution. Let's call it a normal distribution. So there'll be one distribution here. Ideally, we don't know what these are. We haven't seen them, but there'll be one distribution here. Let's say we'll do 4 distributions just for the fun of it. And there'll be some big distribution here like so, and some distribution like that. Okay, so let's impose a generative model like that, right? So we'll come from mu zi sigma zi, where this is a multivariate normal distribution, right? And mu k will come from some prior on mean vectors. We can put a prior on a mean vector. We'll say that we want it to be close to 0 and I times 2, whatever, doesn't matter, right? That one will probably end up screwing me up. How about sigma k? And this is, of course, going to be for all k. So you can write down whatever you want here, right? in the probabilistic programming case, we're going to write down different kinds of models for this, right? So one way of doing this might, so there's a couple. I'll give you a couple examples, right? This could be inverse Wishart. If you're unfamiliar with the inverse Wishart distribution, it doesn't really matter that much, except to say that you should know that it's there and that the multivariate normal inverse Wishart distribution is a conjugate distribution for the covariance matrix of for the mean and covariance matrix of a normal distribution. So there's an inverse Wishart distribution. It's got some parameters, doesn't really matter. Or you could say it's normally distributed about a low rank thing, which would be, the outer product between some number of weight vectors with some, noise on that, or I guess we'd have to be careful with the noise. So there's lots of ways of setting this up. So there's lots of ways of setting up a prior here. The point is, no matter how we do it, we have an inference problem, and the inference problem has to do with like what's the posterior distribution over pi, what's the posterior distribution over z, what's the posterior distribution over mu, what's the posterior distribution over sigma, so on and so forth. And if we want to ask the question about, and okay, so here's the graphical model. We talked about this before. This is the graphical model for a Gaussian mixture model that I used x's instead of y's. I apologize. So that here's what here's what we observe. We observe the y's. We don't know the class labels. I used the z in the previous slide, but same model. The graphical model, which we talked about, is on the left. And we know that we can write down the joint distribution from the graphical model because we know how to do that. We know there's a one-to-one correspondence. We know how to interpret plates and so on and so forth, right? So here's the write out of this big graphical model under these assumptions, where G naught here is just some prior, which I haven't said what it is, but it would make sense for it to be multivariate inverse Wishart in this particular case, multivariate normal inverse Wishart. Okay, so how would you ask the question? Assume that we, how do we ask whether or not two instances of the same class are equivalently similar, right? So the way we do this is we say, are the two instances in the same class? Are they generated from the same mixture component, right? So you can think of these as features of instances or latent classes, whatever. Fine. The point is that the solution is that of wow, I've had this slide this way for years and it's wrong. Is an integral, right? This is one of these inspection things. We have a posterior distribution over all the model parameters, the Gaussian parameters, the class labels, the unknown distribution of classes, so on and so forth, given the observations and whatever prior you have on the individual class distributions, integrating this indicator function, which basically here now we have two discrete quantities, and like, are they the same or not, right? Fine. Does that make sense?
Why is alpha on the other side of the probability? Is that something you set as a prior?
So I didn't. Yeah. So usually, what would happen? So here it is. I haven't put it here, but you can put like a gamma prior. Is a pretty standard thing to do on alpha, right? And then actually you integrate over that as well. So you can integrate over your belief, the strength of your belief about the class distribution, and so on and so forth. Okay? Now, historically, a little bit of like machine learning history and like the ebb and flow of Bayesian versus optimization approaches to machine learning. The choices that one makes, and there's as much as one makes fun of optimization-based machine learning papers being basically historically gradient computation and a small amount of introduction and results associated to that gradient computation. Bayesian machine learning papers, generally speaking, explored the space of models in which many of these the operations, the integration operations that you need to do, could be analytically performed, right? So you would search out and build up the most complex models you could while remaining somewhat tractable. So in this particular case, even though this integration looks really, really nasty, it's actually relatively easy if you know the tricks, if you make the correct choices for priors and you know the tricks from that we just did with the Dirichlet and discrete distribution, because like the multivariate normal is conjugate to the, and the Dirichlet is conjugate, and the gamma in this particular case works out correctly, such that all of these integrals can be done basically in analytic form, except for summing over the class identities, right? So an alternative homework that I could have given instead of LDA, and I was going back and forth in my head, was, you know, write a collapsed Gibbs sampler for a Gaussian mixture model, and it would require you to do all of this analytic integration and these sorts of things just in order to understand. Then the code is trivial; it's super easy to write. Yeah, that's yeah. So the point here is, still, we have models, we have application we might want to do. We formulate models. Those models, if they happen to have the correct conjugate relationships between the distributional families that you assume, might allow you to be able to do analytic integration in order to answer questions inference style, which means like compute posterior distributions and then integrate over those posterior distributions in various ways. So that's like, again, in the same way that we've been doing throughout the course, where I can tell that many of you are like, oh God, what have I gotten into? The point here is to say, really, you want to if you want to frame problems in a Bayesian way, this is a good thing. That the cost is you have to do this kind of integration in order to answer questions of interest. Okay, and there, in certain very limited situations, you can do this integration analytically. Okay. The big question is, how do you build a model for your own problem? And this is one of the strongest selling points for probabilistic programming of anything, is that quite often it's easier for people to think about generative models in programming languages form than it is to think about them in like sticks and balls and distributions that you might not be familiar with. If you don't know what the inverse Wishart distribution is, you're going to have an issue, right? So in this computer science way, a lot of Bayesian machine learning and useful Bayesian machine learning is about mapping your problems onto Bayesian models in which inference is efficient. So LDA is one of the examples. It's a classic example. Inference is efficient. And if you look at the LDA literature, or you think about problems that you might actually be interested in solving, quite often you can reduce those problems to mixed membership modeling, which is basically LDA, and which means that you can reduce your problem to an LDA model and use existing inference algorithms and so on and so forth. Okay, fine. Hopefully that all made sense. I hate talking into a camera. It's horrible. I've also noticed that my nose itches like way more when I'm doing this than I watch some of the video, and I'm like constantly scratching my nose. My nose never itches when I'm not on camera. It's completely ridiculous. But so, you know, everybody should like chime in on the chat channel and be like, Frank, stop scratching your nose. It's unnecessary, but it's itchy as all get out.
Can I ask a question?
Yeah, please.
How much worth, and maybe you'll get into this later in the course, but like how much of your time is it worth in like a probabilistic programming sense to sort of look at where you can analytically integrate things? Like say you have some sort of complicated model, is it worth, you know, sort of spending resources on trying to figure out what parts you could integrate analytically?
So this is an awesome question. There's kind of there's two or three parts to this question, or to the answer. From an estimator efficiency point of view, you should always Rob Blackwellize when you can. In other words, you should always analytically integrate when you can. But there are two places where you could do that, one of which is before you code your model in the probabilistic programming system. That kind of defeats the point of probabilistic programming to a certain extent, which is like you want to be able to just write down whatever you want to write down and then have the system take care of it. The other side, sort of more interesting from a Prog research perspective, is how much effort should the community put into identifying at Prog inference / runtime analytic marginalization opportunities and exploit them. And the answer to that is very complicated, which is to say that there's a very interesting system called Hackaroo. You can look it up. It came out of the University of Indiana, a PL group, that basically attempted to do this to the maximum extent possible. And the reality is the number of situations in which you can do it is incredibly small. So for those of you who are, for those of us who were or are in the Prog language development system, enterprise, whatever, right? The effort that you have to put in order to make this happen is relatively small compared to what you get out of it. Particularly when you move to deep probabilistic programming, which is where actually the only real action is besides bugs and stand. So in bugs and stand, you can go off and do it, and like it's not so bad. But when you start talking about deep probabilistic programming systems, you just can't do this. Like you will never ever come into a situation where you can do this. So the number of, like, why spend 6 months of your life finding compiler optimizations that effectively no programs will ever make use of, right? It's a great question. Cool. So it's the other point to make while we're here is that, like, I've been trying to bring you along in terms of thinking about framing questions as integrals, right? Like here is one of these, inspect the posterior. Of course, the same mistake is here. This should be y, right? Like inspect the posterior, right? Like you give me the probability that these two items are in the same class, right? But what we're going to do is we're going to abandon thinking about specific models or whatever from this point forward and say we're going to start getting general, like we computer scientists, statisticians, and whatever like to do, and we're going to say, okay, cool, this thing up here, it's just an expectation, right? There is some distribution P. It happens to be a posterior distribution, whatever. But in general, what we're gonna think about are expectations where we compute the value of the expected value of a test function, basically. Okay. So when I write E of F, there's an implied P here, and that implied P will usually be apparent from context. Okay. And almost always when I write a variable like X, particularly when we start talking in the Prog context where we get very, very technical, that X is going to be richly structured. It's not a scalar, right? It's going to be some crazy thing. Think vectors, but it's going to get much, much worse when we talk about probabilistic programming, but simultaneously much more awesome. Okay, cool. So what we're going to do today is sampling, and what the homework is about is sampling, and what a large part of probabilistic programming is about is sampling, so that you can compute expectations of this form by sampling from P, even if you don't know P up to, if you only know P up to a normalization constant. Okay. The reason for this is that there's this thing called Monte Carlo integration, which is pretty cool, right? So if you have the ability to sample from this distribution, okay, and remember, this could be a posterior distribution. We don't know. We're going to talk about situations in which this distribution is unnormalized, which means we don't know the normalization constant, but we'll still be able to sample from it. That's critical, right? We can sample XL. If we can do this for a bunch of L's to capital L, then we can form an estimate of the expected value of the function by just averaging the function evaluated at those points. Okay? And when you see this, you go through like at least 3 phases of accepting this. If you haven't seen it before, The first phase is you look at it and you say, oh, that's cool, that seems reasonable. The second phase is you look at it and you say, there's no way in hell this should actually work because it totally doesn't make any sense at all. And then the third way is acceptance, basically, right? Because it does, right? At least in expectation. So the expected value of the estimator f prime, where this expected value is taken over these sampled values xl, is just the expected value of the estimator. But of course, due to the linearity of expectation, 1 over L comes out and the sum comes out, then you're left with the expected value of f of x of L. But since the XLs are by design or by assumption, I should put that here, that's pretty important. Since the XLs are IID, then the expected value of all of these things is the same, so we might as well just refer to it as an X, right? And there are L of them, and that's just when these two things cancel, and that's just the expected value of f. Okay. Cool, that's cool. The even cooler thing is that the variance of our estimator is independent of the dimensionality of x and decreases at a rate of 1 over L, where L is the number of samples you take. Okay. So this is going to show up later on when we talk about streaming or anytime inference algorithms, where you have a sampler that continually generates a sequence of samples. So basically, all of the probabilistic programming evaluators that you build will generate sequences of samples that mean that these expectations converge in this sense. So again, we do the same sort of thing. The variance of the estimator, the laws of variance, or you have a constant, it gets squared, so you get 1 over L squared, and then all the IID all the XLs are IID, so the variance of the sum is the sum of the variances. The XLs are ID, so it's the variance of f of x, and the variance of f of x is just this funny term right here, right? So you look at this, and asymptotically, the variance of this estimator goes to 0 as L increases because of this term right here. But if you look at sort of how squiggly the function is in expectation, right? If f is poorly behaved, or L is small, or the XLs are actually correlated and not IID, then the variance of this estimator might not be good, right? So it's not a panacea. You're not going to win everywhere, but in particular, the last two are nasty for sampling-based inference. But if you can draw approximately IID samples, and you can draw a lot of them, and you can keep drawing more of them, then this thing is going to, and if f isn't, your test function isn't too hairy, then this thing is going to behave pretty nicely, okay? The really important thing is this part. It's independent of the dimensionality of x, and that's really, really critical, right? So we can deal with very, very, very large models, very large parameter spaces, and integrate over them effectively, even though they're big. So it all boils down to sampling. Is this 3:30 to 5 or 3:30 to 5:30? 5, right? Yeah. But all of you want to stay till 5:30 today, I'm sure, right? On a nice, beautiful, sunny day. Yeah, no. This is why I was very confused last time. I was supposed to have more slides last time. I'm like, well, okay, well, I don't have the slides. Well, we'll see what happens. Okay. Anyway, so it all boils down to sampling. So Monte Carlo integration boils down to designing, characterizing, and running samplers. So we'll cover lots of samplers, and we'll do it multiple times so they stick, but we'll do rejection sampling, conditioning via rejection and ancestral sampling, Metropolis Hastings, Gibbs, important sampling, sequential Monte Carlo, so on and so forth. The things we won't cover, except provocatively in at least one of the homeworks, are random number generators and like sampling from standard distributions, which is an interesting endeavor to think about. But let's do very quickly before our break, which is not going to be much of a break today. Let's say that we want to sample from, screw it, let's take a break now. If we want to have the Emma Hansen memorial break, let's take it now. 4:40. I'm not going to get through my stuff today. Thanks, Emma. Appreciate it. All right. See you at 4:40. All right. So it all boils down to sampling. We're back. Welcome back. Okay. Cool. So let's do some sampling, right? And oh, by the way, those of you who are like variational inference weenies already that actually know what's going on with variational inference, of which I know there are several in the course because there's a bunch of them from my group in here. You still, when you have when you want to compute posterior integrals under a non-factorized or variational distribution, you still need to be able to sample, right? And do Monte Carlo integration. So anyway, so let's say we want to sample from some distribution P. And let's say that it's easy to evaluate, but only up to an unknown normalization constant. In other words, P of X is actually some unnormalized probability density P, some unnormalized function P tilde X, which if divided by a constant value, right, ZP, becomes a properly normalized probability density function. Okay. Just to be 100% clear so that we are all on the same page here, right? And I would normally ask, but this is, again, this is, I'll ask. So when is a situation in which we have a P tilde and a P pair? Like, why are we talking about unnormalized density all of a sudden? Jason is spot on. If you see the chat, right? So you know, and I said this, I said it, but I know it won't have landed when I said it, right? Every posterior, every conditional is proportional to the joint. Okay, like that little insight is basically like one of the insights that causes you to fall into the Bayesian reasoning. Like you're like, oh, okay, I can deal with this, right? All I need is the joint, and like I can sort of deal from there. So cool. Now, when we're doing rejection sampling, we also need a proposal distribution, and we're going to talk about proposal distributions all the time through the course, but this is the first time we're going to talk about it. And there's a weird technical condition, and we'll show you an example of one situation in which this is relatively straightforward to satisfy, where there is a positive constant k, which if you multiply by the value of k q of x for all x's, makes it greater than p tilde for all x's. Right? And note, in general, again, x is going to be some richly structured, crazily high dimensional thing. Right? Fine. But we're going to talk in terms of, one-dimensional, two-dimensional plot, one-dimensional distributions and two-dimensional plots, so you can see what's going on. Okay. So if we sample from our proposal distribution Q, okay, so we've got our proposal distribution Q. We're going to draw a sample from Q, right? Let's say that I guess the blue line is Q, and we're going to draw a sample from Q. Here's x tau. Okay, draw a sample from Q, and then we're going to draw a sample from a weird distribution. Okay? It is the uniform distribution between the value 0 and the density of Q evaluated at the value of the sample you just took times the positive constant k, which, if you graphically look at that, is actually this interval right there. We're going to actually draw a value from in there. It could be up here or it could be down here. Okay, cool. And what we're going to say is if this value u tau, jeez, man, u tau is less than p tilde evaluated at the same value, x tau, then x tau is accepted. Otherwise, it's rejected and the process repeats until a sample is accepted. Okay. Now, how does this work? What's going on? This is weird, right? So p tilde is not normalized. Like, what's going on? Okay. Well, it's pretty, like graphically, it's pretty clear what's going on, and that's like the easiest proof for rejection sampling working, right? Clearly, if you sample, you're going to sample from Q. You're going to sample in proportion. Like the number of samples that fall in any particular region is going to be proportional to the area under there, right? But then, for any particular line, the probability of landing anywhere on that line is uniform. So in fact, actually, when you're sampling the pair xt ut, you're sampling a point in this gray space uniformly. Uniform density in this weird space, right? Cool. Which means that if you just simply throw away all the samples that are not in the gray space, but or rather in the gray space, right? Then you're left with uniformly distributed samples over the white space. And if you just throw away the U value, then you have samples that are distributed appropriately under the P tilde curve, or equivalently the P curve. Okay.
Can I ask a question?
Yeah.
How do you find, like, I think that K has to be set such that the proposal is always larger than the target distribution. Is that right? Than the normalized density.
Yep.
So, like, isn't it hard to find K in this case? Like, isn't that sort of half the problem that you need to solve?
So whenever you read about rejection sampling, it's like, how could you ever do this, right? Like, it's dumb, right?
It's only that one slide before GIP sampling and MCMC.
That's right. So, like, I will do you a favor. This may be the only thing that's like, so let me do you a favor and say that, like, the useful thing to think about here is ancestral sampling and rejection to give you posterior samples, basically, right? So let's say we have a model, right? Some of which are some variables which are known, some of which are not. So we'll say the x obs are the observed variables, and x latent will be the latent variable, such that the union of those is x. Okay. So we want, for instance, samples from the posterior distribution of the latents given the observeds. Okay. And I've made it all x here because actually, when we start talking about probabilistic programming, all the variables are going to be x. Well, actually x and y usually, but in some Prog papers, all the variables are x, and there's some that are observed and some that are latent. So it doesn't really matter. They're just random variables. Some of them we know the values of. So we'd like samples from the posterior distribution of latents given the observeds, and that's of course the joint over the marginal probability of the observations, right? Which means that this is, whatever, it's proportional, right? So equivalently, you can write the conditional distribution of interest as an unnormalized distribution, right? Which is just basically P of x, where, x obs is equal to V and 0 elsewhere, right? Does that make sense? So that basically that imposes the constraint that the observed variables are constrained to take values V. Okay? This is unnormalized. That's an unnormalized distribution. Okay? So if you do rejection sampling with Q equal to the joint, like you propose from the joint, you just, in a graphical model, you just ancestrally sample from the joint, then that can be used to generate samples according to the posterior distribution, right? So note that by construction, this Q that we've chosen is always greater than the conditional probability of interest, the unnormalized version, right? Because the unnormalized version, well, because Q of x is 1 times P of x is equal to P of x, which is greater than or equal to P of x times some indicator function, which is 0 or 1. So it's either always equal, it's equal when x obs equals V and 0 otherwise, so it's greater than. And that is the posterior distribution of interest, right? So following the rejection sampling, this rejection sampling recipe yields a posterior conditional sampler via ancestral sampling and rejection, right? So sample, x tau from Q of x. In other words, generate from P via ancestral sampling. Sample U tau between 0 and the density of Q, a value of Q at at x, where Q of x is again is just a joint, right? And then accept if and only if U is below P of x times this indicator function, right? And it can only be below if the indicator function is true, below or equal if it's true, and then repeat, rinse and repeat. So a sample will only ever be accepted when x obs is equal to V, and then it will always be because Q of x equals P of x. Okay, so now we've constructed a situation in which in which we can find the K for rejection sampling, right? And actually, we had a paper come out of the group that, you know, if you're sort of interested in like a modern Prog thing that you that actually has relatively interesting applications for those in the physical sciences or in the simulation-based sciences. It's called Dealing with Simulators That Don't Always Return. So you can think of programs or procedures or whatever that have hard constraints, like if you have stochastic differential equation modeling systems that like fail in certain circumstances, or you have physical simulators that cannot go into certain configurations, and you'd like to be efficient in your simulation, you can frame making efficient simulations as basically the simulator sampling from some joint distribution, and the rejection condition being whenever the simulator fails, whether that's a user-defined condition or a software condition that like restricts the set of the arguments that it can accept. And in that particular case, you can learn a surrogate basically that represents this represents the conditional distribution arising from a rejection sampling algorithm. So you actually, and another thing to say, just to throw it out there, I guess I should put it out there, is that like, actually, this is really important. Like in the first order probabilistic programming language that we're going to talk about, you can't actually write a rejection sampler. But in higher order probabilistic programming languages, and this we'll get to halfway through the term, something like that, within the probabilistic programming system itself, when you write a generative model, most people will write interesting generative models using rejection sampling within the language, right? So in other words, the stable structures and the balanced structures and that sort of stuff, those procedural graphics applications that I suggested. So one part of that is that the actual inference problem is a rejection sampling problem. So we have to have evaluators that can deal with rejection sampling type situations. But another situation is that within the simulation itself, right, there are rejection sampling inner loops that basically say that if you have a part, it has to be mated to another part. And if you put it in space in the wrong way, then you have to just reject that internally, right? So you actually write in your generative model a rejection sampler, and you can do that only in a higher order language. And it turns out that if you follow the standard model example that I gave at the beginning, which I suspect many of you will not, but we'll return to it at the very, very end of the term, and you'll be like, oh, that's pretty cool. Like when high energy physicists build generative models for like how to generate particles with various characteristics, they generate a general particle and then reject, right? So they actually use rejection sampling loops inside of the Sherpa simulator a lot. That's like primarily how generation is done. So there's two reasons to think about rejection sampling and what the distribution is. And one is to program generative models. The other one is to use it as a general purpose inference algorithm. As a general purpose inference algorithm, rejection sampling sucks, basically, right? And it sucks for sort of an obvious reason, which is that, which is this part right here, right? If you're in a space, in a continuous space, then this equality cannot happen. It's a measure zero event, so this is going to fail all the time. It's like pointless almost, right? But it's a building block for other stuff, right? So another way of thinking about it is you can also do like rejection ABC, if you've ever heard of that, or I'm giving you stuff to look up and think about if you want to. But there's a field of Bayesian computation called approximate Bayesian computation, and one thing that you can do is say, well, if my observation is not too far away from V, right? It's in some p-norm ball away, a bounded p-norm ball away, then I'm going to accept the sample. So there's ways to get around the measure zero problem, but it's not pretty. On the other hand, lots of Prog inference problems boiled down to rejection sampling. So you have to be aware that basically that like important sampling reduces to rejection sampling in common cases. So we'll stop with after important sampling, even though I really want to go on because there's lots more, but probably an entire lecture more, which is great. This is one fewer lecture for me to write. So we just did rejection sampling, first sampling algorithm. The second sampling algorithm is important sampling. And important sampling, you really actually think about directly computing the expectation. That's really actually what you're doing. So like any Monte Carlo technique, important sampling approximates the posterior distribution with a set of weighted samples. The trick that important sampling methods rely upon is that we can place an expectation over some nasty thing to form, like the posterior distribution, which is generally hard to sample from, with an expectation over a proposal distribution, again, which we're going to choose to be convenient. Eventually, we'll actually learn. So if we look at an expectation under a posterior distribution of some test function here, R, and X here is latent Y or observes, and this is just exactly how you would write out an expectation, then probably the most important, the most advanced math that I'm really comfortable with is multiplying by 1, which is what happens right here. Okay, I'm really a fan of multiplying by 1, and it's very important in probabilistic programming and modern inference, right? Multiply by 1, right? And then note that this takes the form of an expectation of some other weighted function with respect to Q, this other distribution. So the critical operation is that this distribution has changed to this distribution, but we still have to evaluate this, right? And this is totally fine so long as the posterior and Q are compatible in the sense that's described before, right? Below. Fine. So this works, right? So if we draw samples from Q and define what we'll call importance weights, which are just the evaluation of the posterior density over the proposal density, we can express our Monte Carlo estimate as an average over weighted samples, right? So if we could evaluate the value of this ratio, then the expectation is pretty straightforward. You just plug in the XL values everywhere, resulting in some weights here, right? Fine. Unfortunately, we can't obviously compute this because in the Bayesian inference setting, this posterior distribution is not something that we have access to. Certainly not something that we can score, unless we're in one of the analytic models analytically marginalizable models that we talked about before, like Dirichlet, discrete, something like that. However, we can evaluate the joint, right? Which allows us to define an unnormalized weight. So now this unnormalized weight is the joint over the proposal. And if you just look at what that is relative to the posterior, then there's this factor called the evidence that sits in front times the weight that was computed. So we've got the unnormalized weight and the normalized weight, right? Fine. If we do the substitution then of the posterior distribution with its form, this with the joint divided by the marginal, then the joint sits here, the marginal comes out because it's an integral over X, that's totally fine. And we can now frame this part as unnormalized weights, W, right? Cool. And this nasty thing sitting out here. So now we've done a couple of steps, right? So we've said we can integrate with respect to Q instead of the posterior. Now we're saying we're going to replace the posterior with the joint, but now we have this normalization constant out here, which is nasty, right? Okay. Fine. Well, that's not so bad in some sense, right? Because we can derive an approximation to the evidence by using the same unnormalized weights, by choosing the test function R to be 1. So if we choose the test function R to be 1 and we integrate this over X, right, what's left is an estimate of the marginal probability, P of Y, which is just the normalized sum of the unnormalized weights. Okay? So in other words, if we define our normalization constant estimate as the sum of the unnormalized weights, the average of the unnormalized weights, then Z is an unbiased estimate of the marginal likelihood, right? That's cool. Z hat is So awesome. We can use this to estimate to approximate the normal, estimate and approximate the normalization term in equation 3, which was before, but it's the same thing as before. Which is basically, we just plug in our estimate for this. We have our unnormalized weights here. That's totally fine. We just replace that with 1 over z prime, but 1 over z prime is just the sum over all the unnormalized weights, so we can move that inside. And what we have now are normalized weights and a sum over L of our test function evaluated at samples from Q. So we can evaluate the joint. If we can evaluate the joint, which we usually can, and we will be able to in the Prog context, because we're going to be doing likelihood full inference rather than likelihood free inference, right? Then we can perform important sampling using unnormalized weights. And as a bonus, we get an estimate of the marginal probability as a byproduct of the computation, which is useful for a number of reasons, not least of which it allows us to do Bayesian model selection like we were talking about before. So, oh, I'm late, sorry. I don't think there are any classes after this, are there? Okay, great. Let me finish with these 2 slides and then I'll stop. So the nice thing about this is there's a similar kind of rejection sampling thing going on. So likelihood weighting is a special case of important sampling in which we use the prior as a proposal distribution. So this is Q of X is P of X versus P of XY, or something funny like that, right? The reason that this strategy is known as likelihood weighting is that the unnormalized weight evaluates to the likelihood. So if we have the unnormalized weight, we have the likelihood, we choose Q to be actually the prior, right? Then these terms cancel and what you're left with is the likelihood, right? Okay, cool. So this is foreshadowing homework number 3, actually, right? So where are we? We're kind of doing like old school inference review, Bayesian inference review for homework 1. Have fun, engage, right? Homework 2 is going to be writing FOPL program evaluators. Those program evaluators are going to operate on graphical models. We're going to actually provide the compiler for you this year, which is awesome, right? So you'll get like a structure that you can work with, and you're going to figure out how to evaluate programs in different ways. You're going to write actually interpreters, which is fun. Then homework 3 is writing generic inference algorithms that you can use to run and perform any inference task you want written in the FOPL. And we're going to write a number of these. But if you assume that you can compile a FOPL to a graphical model, like you'll see, you can do that. We know how to do that. We're going to talk about it, right? Then you can implement a generic inference algorithm using likelihood weighting using the following algorithm, right? For each X in the entire graphical model, you just sample from the prior. So you ancestrally sort the graphical model, right? You topologically sort the graphical model, and then ancestrally sample. And then for every observation that you encounter along the way, you accumulate a weight, right? And then from a programming perspective, you'll compute the test function is the return value of the expression. And basically, you can build a streaming inference algorithm using important sampling that continually, well, okay, it's a little bit more complicated when you do streaming, but for a fixed set of particles, you'll get a set of weights and a set of atoms that you can use to evaluate the return, to get a weighted return value from the program, which is to say, you can get a weighted inference result for an arbitrary program, which is to say that you can write down any graphical model you want in a programming language and get an inference result using the algorithms that we have just discussed. Okay, cool. Thank you very much. I look forward to the next time we meet, which will be, I guess, Tuesday. Questions, comments? Was today a little clearer than yesterday or Tuesday, I hope?
Are we supposed to do all the homeworks individually?
It's too bad you weren't here for the first lecture.
Okay.
I would refer to the course website where the policies are explicit and the lecture slides for the first thing. The first homework is meant to be done individually, yes. all of them are meant to be done, to be completed individually, but with more collaboration on the other ones.
Thanks.
Jason, I can't hear you. You're muted.
I feel like we're going slightly fast, but it's okay.
Yeah, but we got a lot to do.
Are there office hours or anything for like homework questions?
As of right now, no. But if you would like me to make office hours, I can. In particular, I can make office hours with Parent very soon. But
I was going to say I can be available next week sometime. This week, no, but next week, yes. If that's acceptable.
I think you've got a couple more weeks anyway before that happens. When I think, you know what I'll do, I'll have my my PA send out a note, since the class is relatively small, and actually poll you to find out when it would actually work to have an office hour, because that makes more sense than me proposing something and it not working for 3 of you and then us doing it 6 times. I'll do that. Is that fair? More questions? This is the best part. We get to actually have conversations after we do this boring lecturing thing, right? Like this is where it's at.
Can I just ask like a quick, maybe stupid question about the assignment?
Sure. Yeah, absolutely. It won't be stupid. I guarantee that other people will have the same question. Yeah.
I just wanted to check my understanding, like for question 3, when you said we should compute the probability 3 ways.
I think I know which one problem 3 is, but yeah, go on. Yeah.
The first way, it's just like this. I think I've done this before, like a standard kind of. You use like the sum rule, and you write out the probabilities. You write like the Bayes rule, and you rearrange things.
Feel free to hop in while I'm looking, Baron, because you've.
Yeah. I believe the first one is just a sort of do it on paper analytically, right?
No, I think the first one is enumerate all possible world states and conditioning by counting which proportion are cloudy given the observed world characteristic, namely that the grass is wet. All right. Is that the one you're talking about?
Yeah.
Okay. So yeah. So great. So does enumerating all possible world states make sense to you?
I can try to guess what it means. It's like you know, the sprinkler's going off and it's raining and the grass is wet and then it's cloudy, and then you kind of like look at the probability that each one of those is true given the other ones are false. Like you use the graph to do all those things. I don't know. I haven't done it in a while.
Yeah. Okay. So all possible world states in this particular case, all of these, there are 4 variables, each one of which is binary. So there are 2 to the 4 possible worlds, right? The suggestion is not to do this by hand, but instead to actually write the code to ingest the CPTs, the conditional probability tables, and enumerate the worlds, but score the probability of each world configuration, right? So that what I want to get you to think about when you're doing this, and like the learning objective here, is to say, okay, what really does it mean for you to, what does it mean for there to be a joint distribution? Like, it means that there are a set of worlds and there's a number associated with each one of those worlds, right? And what does it mean to do conditioning? What it means is to say, okay, we're going to select some set of the worlds, right? And only those worlds which are compatible with our observation are retained. And then basically exactly like that indicator function that I showed today, right? You just throw away all the other worlds. They're incompatible with your evidence, right? Which means that the distribution over possible worlds that's remaining is just a renormalization of the worlds that match the observed characteristic, whether in this particular case is that the grass is wet, right? So really you need a table of 16, you have a table of 16 binary expansions, 0, 0, 0, 0, all the way to 1, 1, 1, 1, 1, and a number associated with those. And then you just look through that table and see which ones the grass is wet in. and renormalize. Yeah.
Yeah, renormalizing, like you sort of do you sum up these different probabilities and then multiply them by
Yep.
something like that, right?
Yep. Bayes rule. Yep.
Yeah. Okay,
that's it's actually that what you're asking is really good, right? Like what does it mean to renormalize? What is normalization doing? Like why are we? It's actually a really interesting thing to think about, right? Like how do you get a conditional probability? What is this like evidence thing, right? And it is you literally sum over the compatible stuff and multiply by that constant, right? Divide through in Bayes rule, but yeah, multiply. Yeah.
Okay. Cool.
And we just talked about ancestral sampling and rejection, right? So that should be now relatively straightforward. Again, code. That one clearly has to be code. You can't do that one with pen and paper, right? And on Tuesday we'll talk about Gibbs sampling, basically. Now, let's see. We can go through this. So, question 1: show the gamma distribution is conjugate to the Poisson distribution. That's the same trick that I just did with the Dirichlet and discrete distribution. Show that the Gibbs transition operator satisfies the detailed balance equation. We'll do that. I'll give you the tools to think about that on Tuesday. 3, now you can do the first 2 on 3. You might not be able to do the Gibbs sampler yet, but again, by Tuesday, you'll have that. The Bayesian linear regression model. Again, on Tuesday, you'll have enough, but that one's going to make you think, right? And it's going to require you to use the tricks associated to like Dirichlet discrete, that sort of thing, right? With normal. So you're going to have to look up in a book somewhere the marginal and conditional probabilities for normal distributions and apply them so that you can derive the correct Gibbs. You can derive simple expressions for the Gibbs updates. And the last
sorry. So we don't need to like do the calculations by hand. We can just plug it into formulas in the book, right?
Show and derive the updates. So I guess derive doesn't mean you have to complete the square. It means that you have to say I am aware of Bayes rule for normal distributions. And apply Bayes rule using for normal distributions. If you've never completed a square, so you don't know what completing the square looks like in a multivariate normal, and you want to be a machine learning person, you should complete the square in the multivariate setting and know what's going on and why those derivations actually work.
Okay.
But that is not required for this homework. But it's required for you to be a machine learning person that has suffered enough to claim to be a real machine learning person. Yeah. And then the last one we've talked about LDA. There's one of the updates necessary to implement said model. But the LDA model, the graphical model, and the distributional assumptions made are in the lecture notes, and you have the conjugacy relationships that will allow you to derive efficient updates. You'll have to do the gamma simplifications on your own. Jason was already complaining about how much work that this homework is. It has served its purpose. Be strong, stay with us, right? Like it will get easier. This is intentionally meant to, make the class not be a very, very large class, because grad classes that are large suck. And also you'll get way more out of it if you understand what's going on in this homework, because we're gonna assume this as a basis, basically. More questions? Thank you. That was a lovely question. Yeah.
I have a question about project ideas.
Yeah.
I'm thinking more towards, or I'm wondering if some ideas are feasible. I just have vague ideas, but I'm thinking about something that's maybe a more theoretical result. I'm thinking about like infinite dimensional probability models, or results that might be more about the optimization of some of these inference algorithms.
Okay, here's an idea straight away in that space that has not been resolved, and I'll give you the examples. So read the Hoppel section in the textbook and understand what's going on.
Okay.
Then read the variational inference paper for higher order probabilistic programming languages by Theophany Weber and David Wingate. And then if you want to do theory, then show that the variational inference algorithm, which is basically an optimization-based algorithm, actually works in infinite dimensional models. So there is an algorithm. Nobody has demonstrated that it is correct.
Okay.
This is monstrously hard and definitely a paper.
Okay.
If you like theory, there you go. Yeah.
Okay. What about cuts in terms of the graphical models? Is that important or not so much?
You can also, if you're interested in like graph cut algorithms, basically for,
Yes.
you can look, so that those apply more in the Markov random field / factor graph land. So you would, and this is honestly the area of Prog that I am weakest in, so caveat emptor, but you should look at infer.net and Tom Minka and my friend, oh no, John Wynn's work on infer.net, and that would be where graph cuts would show up most directly.
Okay.
If you're looking for theory, like there's two other sort of theory kind of things, theory kind of problems that you should stick in the back of your head that you can think about. One is like, what is a notion of d-separation in infinite dimensional models? Like, I think Berend has already asked something about this in an earlier after class chat, right? There is no established notion. Yeah, and if you're, I guess on the optimization side, again, I don't know have you done any formal semantics ever or no?
No.
Okay. This would be a big ask then if you haven't done formal semantics or PL, and I suck at it as well. But a variational semantics in particular for nested queries would be an awesome theory-based project.
Okay.
I expect none of this really actually will make sense at this point, but you know.
Yeah.
In particular, on the last one is yeah, it's cool.
Okay. One more thing about projects, but also related to this lecture. Are we ever interested in dimensionality reduction? Because we had the result that you can estimate integrals irrespective of the dimension.
That we have the result that the variance of the estimate is independent of dimension, but yeah.
But would we ever want to reduce dimension using something like a Johnson-Linden-Strauss algorithm? And you're in probabilistic programming.
I have totally forgotten what that algorithm is. I should know what it is. I do remember, but what is it? Remind me again. Really
you can essentially project like a high dimensional graph into Euclidean space. Using using log n nodes or points, so you can collapse dimension down substantially, and it preserves a metric structure.
Yeah, so that's not going to help in the graphical modeling sense, right? Because unless the metric structure that you want to preserve are conditional independency. Like there's I don't know, I wouldn't know how to map from the conditional independencies that you would want to preserve. That's what basically the graphical model represents, and like whatever metric space you're actually projecting into, if that makes any sense. Like there's something incompatible. So if you're going to take a graph in some Euclidean space and compress it down, and you are going to preserve distances in some sort of a nice way,
Yeah,
that's cool. But if you're going to take a graphical model, right, and compress that down, what you care about is a different notion of distance, right? You want the model to be similar and like preserve conditional independencies or something like that, right? And that notion, I am unfamiliar with. Although there's there's ideas that we could bandy about there for sure. Yeah, having to do with sort of like progressive refinement or something like that, like basically hierarchical models, right?
okay, thank you.
So about that Monte Carlo result, actually, like the idea that the variance is independent of the dimensionality, isn't that only for sort of like the convergence of the variance, or is it also the variance itself?
No, just the convergence. Yeah.
Yeah. So that can be like a very large prefactor associated with dimensionality that you're sort of have to deal with anyway.
Yeah, and the function and exactly. Yeah.
Yeah. Okay.
Greg, you want to recap I will admit that I looked at it and thought nobody's going to think about projects at this point, but it's great that people are. Yeah.
Yeah, I mainly wrote it to see if someone wants to team up.
Did you have a I can't even remember if you had a concrete idea. That's what I'm saying.
Yeah, not really. No, I'm just I'm just trying to do like an application project and something like instruction following in a 3D environment. So
what did you just say? Construction folding in a printing environment? That's what I heard. But
instruction following in a 3D environment. Like if you have like a house or something, and you tell RL agent to kind of pick something, move it somewhere, or find something. So it has to like locate the objects and interact the environment. So I was just thinking at like looking at maybe the Bayesian techniques for RL or something like that. I don't know much about it yet, but
we will do RL as inference. So there's lots of space there. That will be very near the end, but. I'm not sure. I think I put on the syllabus, like the externally available syllabus. Yeah, so if you actually, it's lecture 27, if you look at the readings. So I had various people in my group actually make notes for some of the stuff that we'll talk about later on in the course. And that's one set of notes that's relatively well developed at this point. So you could actually take a look at that and just read it in advance. If you want like the RL as inference and then like how that relates to Prog story, you just read that, right?
Sorry, you said 27? Yeah. But yeah, it says object not found. So could you re-upload it?
No. The overleaf link.
The overleaf. Okay.
Yeah.
All right. Okay, thank you.
Yeah. Anything else? Awesome. All right, gents, lovely to see you all.